Sounds good.
Imagine that you collected some data, and it could be anything. Let's pretend it was the ages of people who lived in a town. You would typically get newborn babies, and maybe you've got somebody who's even 110 years old. But essentially, the kind of shape that you get is roughly a single hill. So you can imagine there'll be lots of examples where that happens, right? Now, when you have this kind of shape, it's called unimodal, which basically means one hill. That's what it means in English, right? Symmetric, which, and it doesn't need to be perfect because it never is. But can you imagine you split the shape? Both halves should look roughly the same. Don't expect miracles, but as long as they're symmetric-ish, right? If you have got those two properties, then you will say that this is a normal distribution. And it's actually a name. It's not me just using the English language and saying, oh, by the way, it's normal. It is a normal distribution. That's its full title. Now, there are two numbers that you need, and only two numbers, to describe everything that's in that picture. Everything. You need to know what the mean is. So let's pretend that this is a town where the average age is 50. Pretty unlikely. Oh, guess what? It's popped back. Pretty unlikely, but it is possible, isn't it? Maybe it's in Florida. I bet you there's some places in Florida where the average age is pretty low, quite high, right? And then the second thing is the standard deviation. And let's say that the standard deviation is 20, just for example. With only those two things, I can then answer lots of questions about this town. I can tell you, for instance, what percentage of people are younger than 30? What percentage of people are older than 70? What percentage of people are between 45 and 52 years old? Now, that's a lot of detail only on two numbers, because these two numbers pretty much tell you everything that you need to know. Some notation. You're going to see those two symbols. The funny thing that looks like that, which you pronounce, it's a Greek letter, mu, and a funny little symbol, it looks like a zero with a little hat on it. Oh, does anybody know what that name is before I scribble it down?
No.
It's called sigma. So when you hear me say sigma, I'm talking about that. And if you hear me say mu, I'm talking about that. Mu is just the formal name for the mean, right? You have a letter of the alphabet. We use Greek letters for them, so that is that one. We also use that one, don't we, for the mean?
Yeah, I've seen that.
Right, and we've used SD for standard deviation. There is a slight difference between those two. X bar is normally used when it's the mean of a sample. In other words, you've only collected 10 people and it's their age and their average age, their mean age is 40 or 50. And when you use the letter mu, you mean the entire population of that town. You know everybody, right? So it's not a sample, it's the entire, it's like a census, right? You've done everything. And standard deviation of everybody is a sigma, whereas standard deviation is that. So let's suppose then that I've got that story and I wanted to know what percentage of people right, let's do three basic questions. Let's do percentage of people who are younger than, then we'll insert a number there in a minute, older than, and between. Okay, somebody give me a number. Younger than what age? You want to know what percentage of people who live in this Florida town are younger than?
40.
40, okay. Older than, give me some other number.
50.
50. God, you have no imagination. I'm not letting you pick this because you'll say 40 and 50. Right, 37 and 82, right? Just random numbers. What I'm going to show you is that you can calculate any of those versions, right? Younger than 22, older than 65. Now, the fact that you can do that, even although all you know is that the mean is 50 and that the standard deviation is 20, and that the shape of the data is a normal distribution. You can calculate any of those things. I can imagine some useful ones. For instance, if we say that 65 is retirement age, I know it's not for everyone, but if we said that, you could find out the percentage of people who are older than 65. So that would give you an idea of how many people in this place are retirees. If you went and said that school children are from 5 to 18, roughly, right? Then couldn't you find the between 5 and 18? And that would tell you the number of children in that town who are of school age. And you can find any of those numbers. So let's go and find younger than 40, okay? So I'm going to have to do a share screen now with a calculator. Now, younger than 40. The calculator has a lovely feature, but it's slightly hidden, and you have to be a little bit careful about it, the way you write it down. But apart from that, you're good. So let's tell you where it's hidden. The guy we're going to use is called normal CDF. Normal CDF. Blue button, there. You see it's hidden in dist. That's short for distributions. Right. Second distribution. Now the guy I want is normal CDF. Do you see it's choice number 2? So you move down to choice number 2, and then you hit enter. Now on the TI84, you get a menu that looks like this. Now our question was people who are younger than 40. Now you have to give a lower number, which is going to go here, and then an upper number that's going to go here. That's going to be the mean, which in this case was 50, and that's going to be the standard deviation, which in this case is 20. Now here's the first little thing. I am going to put in a ridiculously silly big negative number. I'm going to put negative 999 up to 40. That's how I would represent people who are 40 or less. Right, nobody's going to be negative anything in age, but I'm doing that as a general thing because maybe next time it's temperatures you're talking about, right? In which case negative temperatures could arise. Just use that as a placeholder. Whenever you're doing a less than, make this guy negative 999 and that guy's 40. So what this is saying is everybody less than 40. The mean of the town was 50. The standard deviation was 20. You put that package together, you hit enter, and that's what it looks like. Now, if you've got an older calculator, you actually have to type what you see there with all the commas. But hopefully you don't. In fact, use the emulator, in which case you're doing what I'm doing. When you hit enter, do you see that the answer came out as a decimal? 0.308. So in this town, this pretend town in Florida that we're talking about here, 31% of the town are younger than 40. See? And I could change that 40 to 10, to 12, to 59, any number I like. And I could use the same feature in the calculator and I could tell you what percentage of people are in that age group. Can you see how that could be quite useful if you were trying to do an estimate of a town and you wanted to know roughly what it was? You couldn't ask everybody, but couldn't you ask a big enough sample so you could get an idea of what the mean and standard deviation was and use that to approximate it? Now, the government do what's called a census every 10 years. So realistically, they collect all the data, but that's not true. People die and some people don't fill the census, but mostly it works. Right, let's look at the second question. People who are older than 50. People who are older than 50. Well, second distribution. Normal CDF again, enter. Now, I want people to be bigger than 50. So 50 is the smallest, and then everything that's bigger than 50. Well, it could be 80, it could be 90, it could be 100, but I don't use any of those numbers. I use a placeholder number. Any guesses what number I'm going to use to be the upper limit?
999.
Yeah. So you just remember, if you want to put in 7 nines, it really doesn't matter. Now, the good news is that since that question is the same number for mean and standard deviation, I just hit enter. And when I do the paste, I get that. And I get, wow, I get 49.999%, which is 50%. And I have just noticed something that's kind of cool. Remember, this was our town with a mean of 50? And I wanted to know what percentage of people are bigger than 50. Well, if the mean is 50 and the mean is the middle, doesn't it make sense that you would have 50% either side? And what did we find out? Well, when we did the calculation, we found out that the answer was darn close to that, wasn't it? 49.999, which is essentially 50%. Well, let's look at the third possible. 37 to 82. So that's where I'm going this time. 37 to 82. Right, clear this out of the way. Second distribution. Number 2 again. Is anybody here got any questions before I finish this question off? We feel good?
Yeah.
Okay, the lower limit. This is a between story. So the lower limit is 37 and the upper limit is 82. So in a way, it's a little bit easier because you have a real number to use at the start and a real number to use at the end. Does that kind of make sense? If you wanted to know between these two numbers, 37 to 82, the mean is still 50, that's 20. Right, let's see what that answer looks like. About 6 to 8.7%. Pretty cool. Okay. Do another story. Let's suppose that we had a test, we'd given a test, and in this test, the mean was 70 and the standard deviation was 10. And it was a normal distributed test. So right in the middle would be 70. And can you imagine all the numbers going 80, 90, 100? And then going 60, 50, 40, right? And I want to know what percentage of students, right, got a score 90 or above. Now that's sometimes written as like that, percentage or probability that X is greater than or equal to 90. Right, I've got all the numbers I need. Do you think that's going to be a very likely event, or do you think that's going to be quite a small percentage of people who did that? What's your gut feeling for?
Small?
Yeah. You wouldn't expect too many in that test, especially since the mean is at 70, right? And that's what I suspect as well. So let's see what we get. Second distribution, number 2, normal CDF. I want to know bigger than 90, so 90 or above. Oh, look, I put 4 nines in. Makes no difference, it would be the same answer. 70 for the mean, and 10. And yeah, the answer to this is what, 2.3%. Now, I'm going to put this story with another story. Suppose this was Professor A and that was his class. And then there was another class, right, another statistics class taught by a different professor. And the mean was 80 and the standard deviation was 5. And that the distribution was normal. We want to find what's the probability they get a score 90 or above. Now it's a little bit harder to interpret. This test had a higher average, right? 80 is better than 70. But the standard deviation was a lot smaller, which means there isn't an awful lot of variation. In other words, most people got 80 or darn close to 80. Up here, the mean was not as good, 70. But there was a lot of variation here, which meant that there were people who could get all sorts of scores quite a long way from 70, and it still could happen. So here's the question. Do you think that the percentage on that second situation, people who got a score of 90 or above, do you think it's going to be better or worse than the first class? Do you think more than 2.3%, less than 2.3, or do you think it might be pretty much the same? What's your gut feeling? Not sure. Quite hard, isn't it, to tell?
Yeah.
Well, let's find out. 90 or above. The class changed. That's now 80. But that went the other way. So here it goes. And the answer is 2.3%. Which is why some people who think that the mean is all you need to tell how hard or how easy a test is, or how hard it is to get an A with that professor, or how easy it is to get an A. They might just say, what was your average? And somebody says, well, the average in our class was 80. And what was the average in your class? Oh, the average in our class was only 70. Then you're superficially going to think, hey, if I went to the class with an average of 80, I'm probably going to get a better grade. I'm probably going to get an A. Let's just pretend that A's are getting a score of 90 or above. Wouldn't the percentage of people in both classes be the same amount? Only 2.3% of them get A's. And that almost sounds like a contradiction. How can you have a higher average but still get the same number of people who get A's? Kind of interesting, that thought, isn't it? That you might be making decisions based on only the mean, when really your decision should be based on both of them together, because both of them together make a more realistic description of what is actually going on there. I think that's interesting.
I think so too.
Yeah. So you think, if you, whatever the subject is, it doesn't need to be classes. It could be the price of houses in a particular area. Well, if the average price is high but the variation is large, you still might be able to get a house that you can afford. You'll look at the average, I'll say, oh God, Bainbridge Island, the average house is 590,000. I can't afford 590,000. Well, that's probably true, but maybe there's a lot of variation in the price in Bainbridge Island. And maybe you could get a 300,000 house. It probably won't be it'll be a fixer-upper, but it's doable. So, where am I off to next? Well, the next thing we're going to do is look at things called percentiles. Excuse me.
Hey, Professor, I just want to let you know I'm going to head out.
Okay, well, thank you again for dropping in. I'm making some notes on this, so I think they're already online. If not, I'll try and make sure that they do get online for you. It's either notes or a video, I can't remember which. It's probably both.
Okay.
So you'll pick up some of the topics that we missed here. Hopefully that'll make up for it.
All right, thank you very much.
I'll see you Friday.
Yep, see you then. Bye.
So, if you pardon me, I'm going to go out and in again. I'm jumping around here. Are we looking at the TV screen? Yes, we are. We are looking at the calculator screen. Right, now we should be looking at this fella. We're now going to look at things called percentiles. Have any of you did SATs?
No.
No. You've heard about them, right?
Yes.
And when people get SATs, sometimes you'll hear them say, I'm in the 20th percentile, or I'm in the 50th percentile, or I'm in the 4th percentile. Words like that. And you might have wondered what they're talking about. You heard those terms, percentiles?
Yes.
Right. Let's show you what it looks like. Imagine that there's a test, like an SAT test, and the average is 300, and that the standard deviation is 25. If you are in the 15th percentile, you would roughly be about here. The 15th percentile is the number, right, the score you would get in your SAT test that would put you essentially in the bottom 15%. So when you calculate a 15th percentile, the answer you get is a 15th percentile is a score of 227, or the 15th percentile is a score of 290, or whatever it might be. So the 15th percentile, is the score you would get in the test that would put you in the bottom 15%. Now, percentiles are sometimes phrased in different ways. For instance, if I said you were in the 90th percentile, that would be a really, really cool place to be. You imagine we're way up here somewhere, and 90% of the people didn't do as well as you. Of course, there is another way of thinking of that. Couldn't you also say that you were in the top 10%? So the 90th percentile can also be called the top 10%. So sometimes the questions are phrased as a percentile, and sometimes the questions are phrased as a top 10%. In both cases, what you're trying to do is find out what score would I need to be in the top 10%? What score would I need to be in the bottom 15%? So let's find both of those. Let's go for the 15th percentile first. Do a share. Now I'm going into second distribution. Now there are a whole load of guys here, most of which you will never use in your life, unless you do a lot more statistics. That one's nothing to do with us. That one we've used a lot. We're now going to use the guy called the inverse norm. I guess it would have been nicer if they called it the percentile, and that way you'd be able to find it easily. But that's the percentile guy. He's called inverse norm. Now you enter, and it asks you questions in a way that might not be as obvious as you'd want it to be. The first thing it asks you is the area. Now, if you want the 15th percentile, you write the area down as 0.15. If you want the 20th percentile, 0.20. So area becomes percentile written as a decimal. So could you imagine in a big long sentence that said percentile written as a decimal, and you type in your guy there. At least the next two make more sense. The mean is 300 and the standard deviation is 25. Now, do you see this thing here? I wish it wasn't there. It's always on left, leave it on left. And then just, you have to kick down. Right, so you have to use your little cursor, kick down to paste. So percentile as a decimal, the mean, the standard deviation, and then jump to paste. So that's what it would look like in the older calculators. And the answer that comes out is that you would have to be, what, about 274. So let's see what that looks like in my picture. If you were going to get, if you were going to be in the 15th percentile, right, the bottom 15%, you would have to get a score of 274 in that test. Right, I want to be in the top 10% now, right? I want to be the 90th percentile. Let's get this guy. Now the top 10%, right, based on my very badly drawn picture, it's more than 300. Do you think it might be as high as 350? Any guesses before we do it?
Yeah, like 350, 360.
Okay, that sounds, I'm with you. I'm only guessing two, so I don't know anything more than you do. I can't do percentile questions in my head. They're impossible to do in your head, right? The software does it for me, right? So yeah, my gut feeling is that you're probably right, 350, 360. But if I'm wrong, or if we're wrong, it ain't a problem. It's just we're not very good at guessing, right? So let's see what the correct answer ends up being. So I'll clear this guy out the way, and we'll do inverse norm. And I'm going to do a deliberate mistake here. Remember, we're looking for the top 10%. Oh, top 10%. Okay, you turn 10% into a decimal. There we go. I'm ready to continue. Can you see that's a deliberate mistake? What number should I be using for the top 10%?
$90?
Yes. Remember, the 90th percentile is just another way of saying the top 10%. That wasn't meant to be a trick question. So there we go. If you want to be in the top 20%, don't you have to use 80th percentile, 0.80, and so on. Now, enter. Mean is the same, standard thingy, that stays put. Basically, everything can stay where it is. You need 332. Which proves that both of us are very bad at guessing. So if you were looking at someone's SAT score, and the SATs have a kind of mean and standard deviation, and they knew what their SAT score was, you could actually figure out what percentile they were in. And that's kind of helpful, I think. You can work backwards, and as we do here, and find out what kind of score. Why could that be important? I could imagine a situation where you only get into a particular university if you're in the top 20%. And you might say, well, what kind of SAT score is the top 20%, right? I want to know what kind of SAT score I need to get in this test, because that's how they're going to let me in. Well, you could do this, but if you were going to do a top 20%, wouldn't you be looking at an 80th percentile, and you get your calculation that way? So far, so good? Right. Let's do another percentile question, and we'll try and make it medical. Is anybody here in the nursing program? Because I'd like to use some numbers from them if they could. None of you? Okay. So I'll make up something. Totally made up. Let's suppose they have data on the potassium, K is potassium, and the potassium level in a normal adult male is 30. And the standard deviation is 5. Now, where do they get that information? They get it by simply collecting lots of data from people who've had their potassium level recorded. So in a place like America, which has a really big medical industry going, I bet you there's probably millions and millions of results they could now aggregate together and come up with the average and the standard deviation of any blood level virtually that you could think of, right? So you want to know what the hemoglobin level is, you want to know blood pressure, you want to know anything, we've got data on it. We're very good, as a country, we're very good at collecting and using data. So if you've ever had your, maybe you haven't, but I get it all the time because of my age. Whenever I get a blood test, actually I'm going to a doctor's visit today, so she's probably going to suck some blood out of me. You tend to get a number like 37. So your potassium level is 37, right? Let's say that's mine. And then they sometimes have a little thing at the side that says it's high, or it's normal, or it's low. Have you seen those kind of things when you've had any of your blood work done?
Yes.
Right. So you might think, how do they know what's high? Well, let's pretend that in this story, the top 10%, right, is high. So if you're over here and you're one of these people, in that 10% in there, you're high. So we are about to find out what that number is, and then we can use that as a guide of how they would do it in a situation in the medical field. So let's see what that looks like. I'll do a share, I'll do a calculator, do a clear. Okay, so I'll go second distribution, number 3. Now, since it's the top 10%, I can leave this guy alone because that's the 90th percentile. I'm going to change the potassium level now to 30. I'm going to do a standard deviation of 5. And then I'm going to have to scroll down to the paste. And it's 36.4. So what that would mean is that you would, this actually would be true, you would get this number and then they would tell you it was high. And the reason it was high is because my 37, isn't my 37 in the big side of 36.4, right? It's bigger, it's in the 10 percentile place, the top 10% place.
Yes.
Now, you can also get things like what is the normal range that people would get? So when your doctor looks at your potassium or whatever the number is, and they say, what's the normal range so you don't need to worry about it, that's what it should be. Because not every single person has the same everything, right? There is some variation. I think certain parts of your body don't vary a lot. I think your body temperature, if you're normal and there's nothing wrong with you, is a fixed number, right? Give or take very little. But there are other levels within you that change, and therefore it's okay that they're different from each other. But the question is, what would be not normal? What would be a normal range? So let me make up one. Let's suppose that you're doing hormone X, made up name, and the mean of hormone X is on adult males is 70, and that the standard deviation is 3.6, and that it is got the normal distribution. It looks like this. And we want to find out what these numbers are, because this is going to be the normal range. So I'm going to make an assumption here, and it's my assumption, and it may not be valid, but I'm going to assume that the two outside pieces are 20%, and that makes the chunk in the middle 60%. Would that seem to be roughly a reasonable breakdown of, if you're in the middle, that's the normal range. Anything over here is low and the doctor should pay attention to it. Anything up here is also high and your doctor should pay attention to it. But if you're between here and here, hey, that's what you'd expect. Seems reasonable. Now I could widen the window. Couldn't I make the window only the top and bottom 10% at extreme and everything else is normal? But I chose to do this one, so that's one we're going to work with. So I'm now going to do a share, and we'll see what that looks like on the calculator. Right, the first one that I'm going to do is to get the small number, which would be the bottom 20%. Try that again, hit the wrong button. Right, the bottom 20%, where a mean was 70 and the standard deviation was 3.6. And I'll call that 67. Now, while I'm at this, I'll now go in and get the other side. Now, at the other end, there was 20% in it, right? The top 20%. So to find out what you would need to be in the top 20%, isn't that the same as the 80th percentile? Do you see where I'm getting that from? The bottom,
Yes.
right? So you just tweak the number according to the story. Leave everything the same. Everything else stays put apart from that. And at the other side, we're going to get about 73. So as I close out of this window, if you were looking at hormone X in an adult male, the normal range would be that. And you would be considered to have a high level of X if you were bigger than or equal to 73, and you'd have a low of X if you were less than or equal to, what would that be, 67. So if you're wondering where those numbers came from, they came from these calculations, where we know the average value and we know the standard deviation. That was collected through millions upon millions of samples of Americans and probably people in the world, because they share that kind of data. And then once you've got that set up, you can then calculate the percentiles, and that gives you high and low. So one of the things I guess doctors and nurses do, that when you get the blood work back, you tend to scan for things that are different from the norm, things that are higher than they should be or things that are lower than they should be. You don't really get too much information if it's just normal because there's nothing there to pique your attention. And I guess what you do is if there's certain combinations of things that are all high, that might lead you to a conclusion about what might be wrong with that patient, right? So if, making this up, but if their blood pressure is too high and their potassium level is too high and their hemoglobin level is too low, when you put those three things together, it's telling you that this person has got something wrong with their kidneys or may have something wrong with their heart or whatever it is. And that's kind of the detective work that the people in the medical field who have much better knowledge than I have do. But it starts off with data, doesn't it? Doctors don't just typically look at you and say, yeah, it looks like your kidneys aren't working well, without actually doing anything to test you. At least I wouldn't want my doctor to tell me that. And that's about everything I want to do today. Are there any questions?
Not for me.
Right, I hope this has been helpful for you. This video, I'll put it online. It's kind of hit and miss with the videos. Half of them seem to make it, and then the other half, for some reason, just go weird on me. Okay, well, bye-bye everyone. Now, thank you for turning up, and I will see you soon.